Good to know. All right. So we have this week to get through this section, LU decomposition. Um, so I'll see how far I get through these notes today, um, until we run out of time or I just run out of energy. Whichever comes first. Um, Now, as a quick recap, what was established last time was that if you carry out, actually, I'm going to type in this recap right here. Okay. Um, so, all right, so if we carry out gas elimination on an invertible matrix A, um, I want to emphasize without row interchanges, which will be one of the topics I discussed today. A equals LU. It's LU decomposition or LU factorization. All right. So U is the upper triangular row echelon form of A. So just from a process that Gauss elimination carries out to reduce A to upper triangular form, that's your matrix U. And U is L rather, the unit lower triangular matrix and it contains in its lower triangle the multipliers using row operations that were performed during Gauss elimination. So that is so a way to interpret what you have in the LU decomposition. Row J times the IJ entry of L was subtracted from row I in order to eliminate the entry AIJ and then update the rest of the matrix accordingly. And I should clarify. Dang it. All right, so in a Gauss elimination algorithm, like in a text, the multiplier is called MIJ, but that also happens to be the IJ entry of the unit lower triangular factor L. All right, so Gauss elimination naturally gives us this factorization. It's just a matter of how we represent all that work on A that was done. Okay, and then the other thing I was arrived at last time. All right. So now, if you're solving system AX equals B, so you carry out the LU decomposition, and then we solve the system Ly equal to B using forward substitution, and then so the output of that is the unknown vector y. So once we know y from forward substitution, then we solve this system, ux equals y. And since u is upper triangular, we use back substitution for that, and we obtain a solution x. And then if we need to solve ax equals b again with the same matrix but a different right-hand side, this step does not need to be repeated. We just handle these two that are a lot cheaper. So this takes 2/3 n cubed operations, roughly, arithmetic operations. But each of these takes only about n squared. Well, full order of magnitude less. And it's maybe something I already have later in the notes, but actually I'm going to check real quick. So as not to be redundant. Okay. And I'm scrolling through pretty quickly, but I don't see it here. Okay. I want to make a point about storage. Because so L and U, you can store them in one matrix. So you can store U in the upper triangle, including a main diagonal. And the interesting part of L, that's strictly below the main diagonal, I say the interesting part because what's key is we already know that the main diagonal of L is all ones. So there's no need to store that. So you're not storing that. You're not storing portions of either matrix that are zero, certainly. So the non-zero, non-one parts of U and L together fit into an n by n matrix. And one of the homework problems from this section, from section 3.2, requires that. You're modifying a previous function for Gaussian elimination in such a way as to produce the LU decomposition, and the output from that function has to be one matrix that has the relevant parts of L and U stored in that matrix. And in the past, some students have glossed over that part of a problem. They may have carried out Gaussian elimination correctly, but then they don't include the proper storage of L and U, and that's waste. That's actually an important part of that problem. So when you get to that problem, don't blow that off. I will be looking for that. You will lose points. Speaking of homework, in Canvas under homework 2, I know you haven't got to homework 2 yet, but I mentioned a hints file, and I have posted that. So if you go to homework 2 in Canvas, you'll see a PDF of hints. Not on every problem, but certainly the most challenging ones. And I'll do that for later assignments too. Okay. Now, the LU decomposition does not always exist, unfortunately. So I'll give some examples right here of matrices that do not have an LU decomposition. And when you try to compute the LU decomposition by performing Gaussian elimination without any row interchanges, there's a breakdown that occurs. So in the first example here, when you try to eliminate these entries below the main diagonal, the 3 and the 5, you're computing multipliers. And the multiplier is the entry you're trying to eliminate divided by the diagonal entry in the same column. But that's 0. So right away, you're dividing by 0, and the process breaks down immediately before you can eliminate a single entry. Now, for the other example, you can work in the first column, so you compute multipliers of 2 over 1 and then 3 over 1 to eliminate these two entries. But then, when you eliminate this entry, you're taking 2 times the first row and subtracting it from the second row. That's going to introduce a 0 right here. So then you won't be able to, and this entry will become non-zero. So you won't be able to continue Gaussian elimination into the second column. So it doesn't break down immediately, but it does break down. Now, there is a criterion for the LU decomposition existing. It requires that the principal minors of A are all non-zero. I need to explain what a principal minor is, of course. So what you do is you define what are called the leading principal submatrices of A. A1, A2, up to AN. And here's how they're defined. So A1 is just the 1-1 entry. A2 is this upper left 2x2 block of A. And in general, the K by K leading principal submatrix AK comes from taking the upper left K by K submatrix. So I'm taking the first K rows and the first K columns. And that gives me this K by K submatrix. So once you obtain all of these, then you take their determinants. And those are the principal minors. So principal minor is just the determinants of all the leading principal submatrices. If they're all non-zero, then the LU decomposition exists. So to go back to the examples, in the first one, A1 is 0. So its determinant is 0. In the second example, if you look at this 2x2 matrix, 1, 2, 2, 4, if you take the determinant of that, a 2x2 determinant, you're going to get 0. So A2 turns out to be a singular or non-invertible matrix. In other words, the second principal minor is 0. So that's why Gaussian elimination without row interchanges breaks down in these cases, and the LU decomposition doesn't exist. All right, so that is our existence criterion for the LU decomposition. Questions about that before I turn to uniqueness? All right, now let's take a look at uniqueness. So suppose the LU decomposition does exist. In fact, suppose we have 2 such decompositions, L1U1, L2U2, where both L's are unit lower triangular and the U's are upper triangular. Now, A is assumed to be invertible. That means that all of these factors must also be invertible, just because the determinant of a product is a product of a determinants. So I can rearrange. So I can multiply both sides on the right by U2 inverse. So I bring it over here. and also multiply both sides on the left by L1 inverse. Now, here I'm using properties of triangular matrices. That if you multiply two matrices of a certain triangularity, the same triangularity, upper or lower, product will have that triangularity. Also, if you take the inverse, that preserves triangularity. So here we have upper triangular times inverse of upper triangular, which is also upper triangular, and multiply them. So the left side is upper triangular. Similarly, triangularity and uniqueness is preserved over here. So I have unit lower triangular inverted, which is still unit lower triangular, times unit lower triangular is unit lower triangular. So I have upper triangular equals unit lower triangular. But the only way an upper triangular matrix can equal a lower triangular matrix is for both to be diagonal, because here we're saying the lower triangle is 0. Here we're saying the upper triangle is 0. So both triangles must be 0. The diagonal is all that's left. But the diagonal of this matrix is all ones. In other words, this matrix is identity. So we have this situation. But that would mean that L1 equals L2. So then you can go back up here and conclude that U1 equals U2. So when the LU decomposition does exist, it must be unique. So there are a lot of problems in which taking into account the structure of whatever matrices you have enables you to prove certain things like this. It doesn't have a certain triangularity, etc. For questions about uniqueness. Now, once you have the LU decomposition, assuming it does exist, you could use that information to quickly compute the determinant of a matrix using properties of determinants. So the determinant of a product is a product of a determinants. But the determinants of both L and U individually are particularly easy to obtain. Because when you have a matrix that's triangular, upper or lower, it can be shown that the determinant is just a product of the diagonal entries. Well, here the diagonal entries are all 1 in L, so that takes care of that. And then for determinant of U, it's just a product of the diagonal entries. So once you compute the LU decomposition, bam, there's a determinant. Now, in your first linear algebra course, you would have spent time learning how to compute determinants in general, and not using this approach. You'd use a recursive formulation that would where you're deleting rows and columns from a matrix and computing a determinant of a matrix that remains and so forth. And that is an extremely expensive operation. Now, in a class like that, you're only doing it for very small matrices, so it doesn't seem terribly expensive, although it is pretty tedious. But yeah, it's a terribly expensive process. It requires order n factorial arithmetic operations, which is just nuts. You never want to have an algorithm that requires that much expense. Now, computing a determinant using LU decomposition is not cheap. You have to go through the whole Gaussian elimination process that takes 2/3 n cubed operations. And then once you've done that, then you have practically nothing left to do. But still, quite the improvement over n factorial, certainly. Now, a funny thing about determinants, though, is that when you take a regular linear algebra course that's more pure math side of things, a lot of time is spent on determinants. And there's very rich theory behind them. And I remember taking a more advanced linear algebra course. It was actually graduate level as a student, where all these properties that we know about from determinants are proven. And working with, and the definition of determinants deals with uh, permutations and so forth. So there's a lot to unpack there. But determinant doesn't really have such importance when it comes to numerical linear algebra. Now, one thing is key property determinants is that we know that a matrix A is invertible or non-singular if and only if its determinant is non-zero. But that's not really helpful in a numerical setting, because you can have a situation where a matrix A is close to a singular matrix. In other words, only a slight change in the entries would cause it to be singular. But then you can take its determinant and find the determinant is nowhere near zero. Or you could have the flip side of a situation where you can have a matrix whose determinant is very small. So you might think, oh, this matrix is nearly singular, but it turns out it's not. In other words, a small change to A's entries would not cause it to be a singular matrix. And the reason why this distinction is important is because of round-off error. Because you can't really trust the entries of a matrix in a numerical setting, because however those entries were obtained, you should count on them being at least slightly erroneous. So a better way to measure whether a matrix is almost singular or almost non-invertible is not the determinant. There are other ways to measure that in terms of that are appropriate metrics. So if you're familiar with the concept of a norm from other courses, and we will deal with norms later. Norm is a measure of magnitude. For example, Euclidean distance is so the norm of a vector that you're accustomed to, the square root of sum of squares of its components. That is an example of a norm. And the determinant is in no sense, even if you take the absolute value of it, it is in no sense a norm. So it's not a really good judge of distance between a matrix and a set of singular matrices. We do have other ways of measuring out, which I won't get into now. My point is that the determinant, as much time as I'm spending on today, not really a big deal in numerical linear algebra, as a contrast from what you see in classes like 326, where a huge deal is made out of it. Now, so I mentioned that the LU decomposition does not always exist. But if we have a matrix for which it doesn't exist, we still want to take advantage of it somehow. It just means that to carry out Gaussian elimination, we must carry out row interchanges. And then we're still going to obtain an LU decomposition. It's just not going to be the original A. But we can still use that to solve systems of equations. And that brings me to pivoting. Now, pivoting simply it refers to interchanges, mostly of rows, but column interchanges can also be called for. Now, I've described a situation where it's maybe absolutely necessary to carry out row interchanges, but it turns out that's not the only reason for such interchanges. Again, in a numerical setting. So this is another contrast with what you would have seen in another linear algebra course. What I'm showing you here is the main step of Gaussian elimination. This is how we carry out a row operation. We have row I is equal to itself minus some multiplier times row j. But in contrast to before, I've added these superscripts. So if I call A1 the original matrix, and then A2 is the matrix you get after you've worked on the first column, and A3 is what you get after working on the second column, and so forth, we have different versions of A that start from the original and go all the way to where it's reduced to upper triangular form. So this is version J of a matrix, this is version J plus 1. This is the update, where we're working on column J to eliminate its subdiagonal entries. So when this step is performed throughout Gaussian elimination, because of rounding error, this entry here is already going to have some error in it. In other words, you can think of it as being contaminated with round-off error. Now, a way to describe it, to account for round-off error carefully, is to think of it this way. Here's the entry that you have after your computation. Here's the entry you would have if you were able to perform exact arithmetic. And then it's multiplied by this factor that includes some relative error that's due to rounding. So this is generally going to be a very small quantity, but we do have to consider it. Now, because there's already some error in this entry, that error gets multiplied by this multiplier. What if a multiplier is large? Then this error in this entry that may have been extremely small, maybe it's on the order of 10 to the minus 16th or something like that, now becomes large and contaminates this entry even more. Right, and that's the point that I'm making here. So that means that to make sure that rounding error doesn't unduly affect Gaussian elimination, you want to try to keep the multipliers Mij small. So that way, whatever error you have in previous computations is not unnecessarily amplified. So how do we do that? Well, the answer is suggested by a formula for a multiplier. The entry you're trying to eliminate divided by the diagonal entry in that same column. So if we can somehow ensure that this entry is larger than all the ones in that column, then we can guarantee that these multipliers are less than or equal to 1 in magnitude. So that will certainly help contain that round-off error. And this leads to what is called partial pivoting. So in partial pivoting, you're about to work on a column J. Here's your diagonal entry in that column, and here are all the entries below it that you're about to eliminate. So what you do is you examine all of these, you iterate over all of them, you do comparisons, and you find which one is the largest in absolute value. So let's suppose that one of these entries, say in row Q, is the largest of this bunch. So then you go ahead and swap row Q and row J to move this entry into the diagonal position. So that's going to guarantee that the multipliers are at most 1 in magnitude. Now, this does add some overhead to Gaussian elimination, but it's a reasonable amount of overhead because, for instance, in the first column, to make this determination of which is largest, you're performing about n comparisons. Then in the second column, n minus 1, then n minus 2, and so forth. So overall, you're performing order n squared comparisons to figure out which rows to interchange. And you're going to interchange you're going to perform at most n minus 1 interchanges, one for each column. And so you're performing order n squared comparisons, moving around order n squared elements in total. And that is negligible compared to the order n cubed work you're doing for the arithmetic of Gaussian elimination. So yes, it's adding something, but it's not much in the whole scheme of things, especially for a large matrix. So while there are different pivoting schemes out there, and this is not the only one I'll tell you about, this is by far the most popular because It does a good job in terms of reducing round-off error, and it's efficient. So in fact, when you use a backslash operator to solve a system of equations, if you're doing a\b to solve ax equals b, under the hood, that's what it's doing. It's performing Gaussian elimination with partial pivoting. So that's like a default algorithm for solving ax equals b. But it's not always effective. It can happen that even when you use partial pivoting, even though the multipliers will get small, the entries of u can still get very large, and that's still a problem, because when you go to perform back substitution later, then you're multiplying elements of your solution by entries of u, and in fact, if those are large, that again will amplify whatever round-off error is there. So we like to have the entries of both L and U be of a reasonable size. And unfortunately, partial pivoting cannot guarantee that. And there's a homework problem for this section that illustrates the point. There are questions about partial pivoting. So considering one of the homework problems, you'll carry this out by hand. Remember, you don't check the whole column. You start at the diagonal entry, and everything below it is what you consider. You're finding the largest of those. But then when you swap rows, you determine which rows to swap. Don't forget to swap the whole row. Now, to the left of column J, those rows will be 0 anyway, but still. I'll take a little time to talk about another well-known, often used pivoting scheme called complete pivoting. So in partial pivoting, you're only checking a portion of one column of your matrix. In complete pivoting, you're examining not just rows j plus 1 down to the bottom, but also those same columns. So you have a whole portion of a matrix, a whole submatrix to search. And you're finding the largest entry in that whole submatrix. So you find what entry that is, and let's suppose that you find it in columns P and Q. And both of these have to be at least J, because that's a portion of a matrix and you're searching it. So you swap rows J and P, like in partial pivoting, but also columns J and Q. You're swapping rows and columns. So another way of putting it is A gets replaced by this matrix, where you're multiplying on the left by a permutation matrix to swap rows. You're multiplying on the right by a permutation matrix to swap columns. Here's an example of a permutation matrix. So this matrix has the effect of swapping row 2 and row 4. So it's going to put row 2 into 4th position, row 4 into 2nd position. Now, the way this is figured out is, it's kind of like, it's just like elementary row matrices. Because a row operation during Gaussian elimination can be thought of as multiplying by an elementary row matrix. How do you get the elementary row matrix? You perform the operation on the identity matrix. So if you took the identity matrix of 4x4 and swapped rows 2 and 4, this is exactly the matrix you would get. So if you multiply on the left, it'll swap those rows. But if you take this same matrix and multiply some matrix by this on the right, it will swap those columns, because this is also columns 2 and 4 of identity swapped. So, so for example, if you found the largest entry in so for example, row 2, column 4. Oh wait, yeah. Oh, sorry. If j is equal to, sorry, I completely messed that up. If j is equal to 2, you're working on the second column, but in the 4-4 entry is where you find the largest, then you would use this matrix to carry out the swaps by multiplying on the left and the right. So permutation matrices are very helpful for describing what happens in Gaussian elimination when it comes to row, usually row, but also column interchanges. So all they are is scrambling rows or columns of identity to describe how it would act on a general matrix. So now, if you're replacing A by this, what happens to the system of equations you're trying to solve? Well, what I would do here is I would take this system I'm trying to solve, multiply both sides on the left by P1, and then between A and X, I would introduce P2, P2 inverse, because this is identity. So in other words, this system of equations is equivalent to the original. So now, if I define A tilde to be this portion, P1, A, P2, that's the new matrix of the system. It has the rows and columns swapped. And then if I define B tilde, the right-hand side, the new right-hand side, to be this vector here, so it has the original right-hand side B with the row interchanges performed on it. And then my new solution is P2 inverse times the original solution. So what I'm going to do is, after I perform my pivoting, I'm going to solve this system that has the interchanges taken into account. So I compute the LU factorization, go ahead and solve the same systems as before, and I obtain the solution X tilde. But I don't want X tilde. I want X. So I use this relationship rearranged here to get X. So all I end up doing is end up rearranging components of this solution of a modified problem to get my solution to the original problem. So questions of how we deal with complete pivoting and how we solve a system in that case. Now, whereas complete pivoting involves both row and column interchanges, here expressed using permutation matrices, partial pivoting, which does only row interchanges, that can also be described using permutation matrices, but that's something I'll get into much more a bit later on. Now, it turns out there are good reasons to perform complete pivoting or not. Because on the one hand, on the pro side, you do get even smaller multipliers because you're searching a larger portion of a matrix for row and column swap with. So multipliers will be smaller in magnitude or no larger in magnitude but likely smaller than what you would get from partial pivoting. So it does help reduce round-off error even further. And it has been proven that Gaussian elimination is what's said to be backward stable. And what I mean by backward stable, this gets to a concept covered last semester in the 460-560, backward error analysis. In backward error analysis, you're assuming that your computed solution is the exact solution of a nearby problem. And the trouble is that doesn't always hold. It only holds if your algorithm is said to be stable. Now, so when you use complete pivoting, it has been proven that Gaussian elimination with complete pivoting really is backward stable. That is not true necessarily for partial pivoting, but it works often enough that it's the most partial pivoting is the most often used pivoting method. Now, when the backward error was discussed last semester, we have this relationship. A forward error, the error in your output, is backward error, which is the error in your input, times the condition number. Now, last semester we saw a general definition of condition number. Later in this chapter, I'll show you a definition of condition number specifically for a problem AX equals B. Now, this proof of backward stability is actually a really big deal. And the reason why is when electronic computers were first invented, and I emphasize electronic computers because before we had them, the word computer referred to, it was a job title for a person. So you had, so people were employed as computers for instance, by the Department of Agriculture to solve systems of linear equations by hand. So they were doing all their computations, they were sitting at their desk, grinding away on the numbers. And that's what a computer was until electronic computers came along. So a person working as a computer could, within reason anyway, work with exact arithmetic. They could use fractions or decimals as needed. But electronic computers were using floating point arithmetic from the beginning. And that's what led to every operation pretty much incurring some error. So that was the big trade-off, that although more operations could be performed per unit of time, now those operations were wrong to some extent. So back then, in the early days of electronic computers, there was a lot of concern that Gaussian elimination, which had already been used for like literally thousands of years by that time, by hand, would not be suitable for electronic computers because of the accumulation of round-off error, rendering a process numerically unstable. And there were a lot of people back then who sincerely believed that it was unstable. And considering that solving system linear equations is a cornerstone of so many numerical methods, countless numerical methods, what if you could not use the main tool for it, Gaussian elimination? What would you do? Now, there is an answer that one could try using iterative methods instead, and we will learn about something about iterative methods later on when we get to chapter 5. And there are a lot of cases where iterative methods really are the best way to go, but Gaussian elimination is still of vital importance. So it was a legendary figure in numerical linear algebra, Jim Wilkinson, who performed the first careful round-off error analysis of Gaussian elimination to prove, at least under the right circumstances, that it really is, in fact, numerically stable. And so that pushed the issue to rest and made people feel comfortable with using Gaussian elimination on electronic computers. That's why theory in such an applied discipline like numerical analysis is still very important. People need that guarantee. And it's guarantees like that, when available, that guide the development and use of mathematical software. And if you come up with some algorithm and you can't provide any assurance, even under certain circumstances, that it will work, people are not going to feel comfortable using it. They'd be searching for an alternative. So this is the upside of complete pivoting, that it has greater stability, provably so, than partial pivoting. But on the downside, a lot more expensive, because now you're sifting through a submatrix rather than a portion of a column to find a row and column to swap with. So now the number of comparisons jumps to order n cubed rather than order n squared. So the overhead involved becomes a lot more significant. That's a key reason why, really it's the reason why complete pivoting is not used as much. Now, I do have more notes here, but what follows is not easy to digest. It's not something that I would want to rush. So I think this is a natural stopping point as far as going through the notes is concerned, and I certainly have enough time on Wednesday to do the rest. But that also means that we have a good amount of time for any questions, like on the homework. Are there any? It's easier to determine how long to let the awkward silence last when it's in person, not so much when it's virtual. Any homework questions at all? Oh, 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 yes. Thank you. I wasn't feeling so great on the weekend, but feel fine now. Thank you. Okay. All right, then I think I'll call it good. And then, of course, you can ask questions of me anytime afterwards, or you can save it for Wednesday. So until then.